So now let's go on the last part, which is CPU optimization. So let's start by laying down the context. Historically, a CPU was a physical component located on the motherboard. With the quick evolution of technologies with multi-core, hyper-threading, hardware, and software naming, the term CPU is difficult to map to a single concept. On our server, we use AMD EPYC 7502 Zen 2 CPUs. The reason for this choice is to have the best ratio performance, power, and cost. And this CPU is well adapted for virtualization and high-performance computing workloads. So in this image, you can see a near-infrared photograph of the CPU. Let's now dissect the different parts. If you look at the image, I've highlighted two parts. So the first part is a core complex die, CCD. It's a chiplet that contains up to 8 CPU cores. It provides the computing power. And in the middle, you have the I/O die, a chip with no cores, only I/O functions. And its role is to connect the CPU cores to memory, storage, and other devices. And it also ties the 4 CCDs together. And the CCDs are composed of core complex, which are CCX, and you have 2 per CCD. And a CCX is a group of core which within a CCD sharing cache. This allows fast data sharing between cores. So each CCX contains 4 CPU cores. It starts from 1 to 4 on the left and goes up to 29 to 32 on the bottom right, which gives a total of 32 CPU cores. So you might wonder why I'm showing you all of this. Simply because data sharing across CPU could be expensive. Indeed, if you consider T being the data latency between 2 CPU within the same CCX, sharing data across CPU CCX within the same CCD is 4 times higher, and across different CCDs is 6 times higher. On our server, we dedicated the last CPU, here CPU 32, to the control plane components. So here, I showed you earlier that we had some provisioner, and they are pinned on the CPU 32. The reason we do that is to avoid messing up with HAProxy processes. So our current configuration is pretty simple. We allocate 31 threads and 1 thread per core, right? So our intention was to avoid thread starvation. Therefore, attributing 1 thread per CPU one CPU per thread was acceptable. So here's a capture of the htop command of one of our server. You can see that each CPU is attached to 1 CPU core. Sorry, each thread is attached to 1 CPU core. And the last CPU, CPU 31, because it starts from 0, runs our control plane. And also it starts the command using systemd. Also, if you remember the architecture I showed you earlier, we have a varnish instance installed on the same server as HAProxy, which explains the usage of the RAM. So knowing all this, our aim is to always get the best of the system resources. Therefore, we started to test a recent feature introduced by HAProxy. In HAProxy 3.2, which has been released last week, there are some options to control the CPU. Allocation policy in an automatic way. Here we have the following. We drop CPU 31 and we do a group by 2 clusters. And this is equivalent to the following. So if you want to type it, you can do it even in version before 3.1. And it can kind of sound complex, but if you look at the image, it pretty much looks, this is the thread group 1 and 2, 3, and 4, the stuff I put in blue. So in total, we have 4 thread groups. Each one has 8 cores, except the last one, which has 7. And in the binary, there's an option to display the thread bindings from the configuration. This helps to get an idea of the config that will be applied at runtime. So we applied the exact same load on a reference node with our nominal configuration, which is 1 thread per core. So using an equivalent traffic, we observed that the node with 4 thread group was using less CPU. This is not a lot, but we can sense that there's a lot of room for improvement and for optimization. And if you look at the context switching, we observe a gain of 20%, which clearly explained by the CPU grouping by CCD, since it doesn't have to go across all the IO die. If you remember the image I showed you like 4 slides before. I know that it's late, but. So as a conclusion, we can say that we will continue experimenting to have the best configuration that works for us. Clearly having policy with auto-computing abstracts complexity. So I invite you to try it. And there's an open discussion on GitHub to gather feedbacks in case you want to try it.